Lesson 10. Add and subtract fractions. In this lesson, we're going to review vocabulary, discuss the idea of benchmarks, add fractions with different denominators, subtract fractions with different denominators, and model adding and subtracting fractions with an area model. So this is a little different from 4th grade because the denominators are different. In 4th grade, they were the same. So for the vocabulary, the numerator is the number that sits on top. So if I was to look at 1/2, the numerator would be the 1. And the denominator is the number on the bottom of our fraction bar, and that's the 2 in this case. Now, common denominator means a denominator, so the bottom number that they have in common. So, for example, I might have 2/4, and 1/4. They share a common denominator. Throughout the lesson, we're going to be searching for those common denominators. That is really what your main goal is before you can start adding or subtracting fractions. That's what makes it so different for a lot of kids, is that we're not used to having to change the denominators, but we will because we need them to be the same denominator before we can start adding and subtracting. And finally, equivalent fractions, which means the fractions are of equal value. They may have different names but have the same value. If you remember from decimals, some decimals also have different names. We say them differently, but they actually have the same value. So for fractions, equivalent fractions, you might see 1/2 is equal to 2/4. So those have completely different words attached to them, but they have the same value, as you're going to see as we move on. So when we have the same value, that's where you get the word equivalent. Okay, that should sound familiar. Okay, so our new vocabulary, well, not new, but reviewed vocabulary should be numerator, denominator, common denominator, and equivalent fractions. So here we have the an example of all the fractions that we will be using in class. We're missing the 20ths, I think, but these are the ones you'll see the most often in your textbook and in your homework. So as you can see, 1/2 is the same thing, is equivalent to 2/2 or 3/3 or 4/4, and it continues all the way down like that. So if you're looking at a fraction and it has the same number on the top and the same number on the bottom, that means it's complete, it's full. Okay, it means it's 1/2. If you see the numerator is larger, if the numerator is larger than the denominator, that means we have more than a whole. Okay, and we call this kind of number an improper fraction. When this happens, we can take those numbers out, so we can see that 6/5 is more than 1/2. So we say that that's 1/2, and a 1/5 is left over. And this kind of number we call a mixed fraction because it has a whole number and a fraction. It is mixed. It has both parts. So let's talk about benchmarks before we move on. A benchmark is a type of fraction that we know by heart. We just love them, and they help us understand fractions a little bit better. So our first benchmark will be the number 0. We all know what that looks like. We all know what it looks like when there's nothing there. We also know what it looks like when it's full, the number 1. Or the number 2 or number 3. We know what whole numbers look like. We know that when we look at a picture, if all the boxes are shaded in or none of the boxes are shaded in. So those are our benchmarks, 0 and any whole number. The final benchmark is the half benchmark. So right here. The half benchmark lets us know if we're approaching a whole number or are we closer to 0. And the half benchmark is really, really helpful in general. It's just something that is really good to know. So here are the halves. So 1/2 is the same as 2/4. It's the same as 3/6 and 4/8 and 5/10 and 6/12, and there's about an infinite amount more of fractions that are the same as 1/2 with different names. So our benchmarks again are 0, 1/2, and any whole number. Okay, so and any half. So if it's 1.5, that's a benchmark. 2.5, 53.5, 1,000.5 will be a benchmark as well. So here's a really good example of equivalent fractions. So as you can see, the same circle is repeated, but cut into different size pieces. So the first circle is cut into halves. The second one is cut into fourths or quarters. The third is cut into sixths. And the last one is cut into eighths. As you can see, they all take up the same amount of space in the world. They have the same value. So these fractions are what we call equivalent fractions. And this is really, really helpful when we're adding and subtracting. So be on the lookout for these lovely equivalent fractions. The halves are the nicest things to know. It really is helpful later on. So here's our first problem. So we have 4/10 plus 1/5. Okay, so the first thing we need to understand is we will never, ever add two denominators. Not like this. So what I see a lot of 5th graders do when they first approach this, they do, well, that's 5 and that's 15. That is not how you do that. And I'm going to show you why really quickly. So if I have 4/10, so I have my tenths, 1, 2, 5, 7, 9. So if I have 4/10 and I want to add a 5th to it, okay, so I'm going to divide this one into 5ths. They're not perfect, but you gotta get the idea. So I'm going to shade them in so you can see what that should look like. Come on. So I have 4/10. I'm going to try to shade in 4/10 as best as I can. And I'm also going to shade in 1/5. 1, 2, 3, 4, 5. Oops, that's way too many. Alright, so we have 4/10 plus 1/5. Now as you can see, if I add those two green spots together, they should be getting bigger. Like the total amount of green should be getting bigger. I can even try and move this green. It would work. And I'm going to show you what 5/15 looks like. So I'm going to try and do a bar that's about the same size. Not perfect, but we do what we can. I'm going to try to do 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, let's try to find space, 14. So that's 15 in total. And let me try and show you what 5/15 looks like. So I'm going to try to shade in 1, 2, 3, 4, 1, 2, 3, 4, and 5. So as you can see, 5/15 is not very big at all. It's not even halfway up the bar. Whereas 4/10 and 1/5, if I put these two green spots together, if I try to move this green spot here, inside that, you know it's going to come up to about this high. If I add these two together, it's going to increase and grow. That is not the same thing as 5/15. 5/15 is actually really small. It's less than half. But 4/10 is more than half. 4/10 plus 1/5 is more than half. So that's just a really quick way of showing you that if you add denominators that are different and try to do it as quickly as possible, you are getting a very, very wrong answer. So let me show you how to do it correctly. So the first thing I'm going to do is erase that really icky answer, because that is not true. Okay. So here we have 4/10 plus 1/5. The problem, of course, is they do not have the same denominator. We need them to have the same denominator. When the denominators are the same, life is so much easier. So the first thing I'm going to do, I'm going to say to myself, well, do I see any whole numbers there? No, I don't have any, so I can move on. I have 4/10 plus 1/5, which lets me know that I have a denominator. I have a fraction that's cut into 10, and I have another fraction that's cut into fifths. What I need to do is make sure they have the same amount of pieces. So in order to do that, I'm going to figure out how to cut these two denominators so that they are the same thing. And I do that by listing the multiples of the two denominators. So I put them on this chart, and I say to myself, well, what are the multiples of 10? So that means I'm going to do 10 times 1, 10 times 2, 10 times 3, and I'm going to do the same thing for 5. And when I see something that's the same or something in common, I'm going to stop. So 5 is my first multiple. 5, 10. Oop, there it is. I see something that's in common. And this is when I can stop. So I see that the 10 is what they have in common. So that means I'm going to have a denominator with 10. Well, luckily, 4/10 is already in 10 pieces. So what I'm going to do is show you, it only took me one multiple to get there, so I'm going to tell myself, hey, I only multiplied once, so I need to multiply by 1 over 1. Okay, this really builds good habits. We know that it's going to stay the same, but it's a good habit to write this down every single time. And for the 1/5, well, how many times did it take for me to get to 10? Let's see, 1, 2. It took me 2 multiples to get to 10. So that means I'm going to take 1/5 and multiply it by 2 halves. And what we'll see is something pretty great. It's going to get us right where we need to be. So I know that my denominator that I'm going to get needs to be, both of them need to be 10. So let's do the work. So 4 times 1 is 4. 10 times 1 is 10. Plus 1 times 2 is 2. 5 times 2 is 10. Perfect. This is the best place to be. Both fractions have the same last name, 4/10 and 2/10. Well, what's 4/10 plus 2 more tenths? The answer is 6/10. So just to review, make sure that you're not adding your denominators. Check for whole numbers. If you don't see any, then you can continue. Make a list of the multiples of your different denominators and stop when you see something that's in common. Figure out how many multiples it took to get to that perfect common denominator, and multiply the numerator and the denominator by that amount. When you've done the multiplication, you can add up your fractions and you will get a wonderful answer. So here's another example. This time we do have whole numbers, and that is going to give us another step, which is fine. We know what we're doing. So the first thing I want to do is see what my denominators are. They are different, so I'm going to have to figure out what my common denominator will be. That comes in a moment. What we really need to do is change these whole numbers, because what if I really just want all my fractions to look very similar, because it's going to make it easier for me to add. So I'm actually going to change the two wholes into fourths. Well, how many fourths are in one whole? How many fourths are in two? So I'm going to say to myself, well, there's 4 in this little circle and 4 in this hole. So I have two holes. I'm drawing them so you can see. 4 plus 4 is 8. There are 8 total fourths in 2 and 3/4. Well, in 2 holes, sorry. There are 8 in 2 holes, and the total fraction is 8/4 plus 3/4. I'm going to do the same thing to the one over here. This fraction is in halves, or there's a 2 at the bottom. So how many halves are in one whole? Well, I have one hole, so I'm going to draw 1 and put a 2 inside. There's only 2 in there. So I'm going to do 2 halves plus 1 half. And that's what's inside that fraction. I'm going to add them together so that I don't have to work with 2 fractions at a time. I don't want to work with 4. So what I'm going to do is 8 plus 3 is 11/4. And then 2 plus 1 is 3 halves. We still have different denominators, but at least we got rid of our whole numbers. Now that the denominators are different, we're going to have to set up a chart and see what they have in common. So I have 4, 8, 12. And I have 2, 4. Oh, I see something in common. 4. How many times did I have to multiply to get to 4 for my 11/4? Just once. So I'm actually going to rewrite it over here. 11/4 multiplied by just 1, because I only needed to jump 1 time down my chart. So 1 whole. And then how many jumps did it take for me to get to 4 for my halves? 1, 2. 2 jumps. So I'm going to multiply my 3 halves by 2 halves. Okay, so now I can do my math. I have 11/4, because 11 times 1 is 11, and 4 times 1 is 4. I'm going to add 3 times 2 is 6, and 2 times 2 is 4. So 11 plus 6 is 17, and the 4 stays the same. We have 17/4. 11/4 plus 6 more fourths is 17/4. You could leave it this way, or you could say, well, what's 17 divided by 4? Because that's what that bar means. It is a division bar as well. 17 divided by 4. Well, that would be 4 and 1/4. Because there are 4 groups of 4 in 17. And 1/4 left over. So there are 2 ways to answer this problem. You can answer it as a mixed number or as an improper fraction. Now to subtract fractions. The methods are actually really similar. Let's begin. So I see that my denominators are different. I don't have any whole numbers, so that kind of makes it easier too. So I'm going to set up my chart. I need to know what 5 and 3 have in common. 5, 10, 15. All I'm doing is adding 5 each time. And for the 3, I'm going to do 3, 6, 9, 12, 15. 15 is what they have in common. So that means both of my numbers have to change this time. 4/5 is going to change, and so is 1/3. How many jumps did it take for me to get to 15? 1, 2, 3. And I'm going to remind myself, 3 jumps. So I'm going to multiply by 3/3. And I'm going to put it in a box to remind me that these belong together. And I'm going to do the same thing for 1/3. How many jumps did it take to get to 15? 1, 2, 3, 4, 5 jumps. So I would actually have to, if I had 1/3 in a picture, I would have to cut it 5 times so that it would be 15ths. So I'm going to multiply by 5/5 and put that in its own box. Now I'm ready to subtract. So I have 4 times 3 is 12, and 5 times 3 is 15. 1 times 5 is 5. 3 times 5 is 15. Wonderful, they have the same last name, 12/15 and 5/15. 12 minus 5 is 7. And the denominator always stays the same after that, 15ths. The answer is 7/15. So it is a really, really similar strategy, except this time we're subtracting. Here's another example. This time there's a whole number in front. So this is when it's really important that you change your whole numbers over. And I'll show you why. So I have 3/2 and 3 3.5 minus 1 3/5. I can already see that my denominators are different. The first thing I want to do is, how many halves are sitting in 3 holes? So I'm going to take the denominator and say, well, I know there's 2 pieces in that hole, 2 pieces in that, and 2 pieces in that. So 2 plus 2 plus 2, that's 6. So that's 6 halves living in there. And the half that was sitting there already. So that's why we do the whole number. We really need to break apart the whole number to see exactly what's living inside. And then this one is 1 3/5. So this one's broken into fifths. How many fifths are living in one whole? If you said 5, you are right. And with the 3/5 that were already living there. And we put that in a box to keep them together. So let's put this all together. We have 7 halves minus, because this is a subtraction problem, 8/5. Alright, so let's get started. We have a 2 and a 5. So we're going to put that on our chart. What do 2 and 5 have in common? Let's find out. 2. Oopsie daisy. 2, 4, 6, 8. I don't see anything yet. 5, 10. Maybe I need to go a little bit longer in the 2. There it is. 10. 10 is what they have in common. So how many jumps did it take? How many jumps down the chart did it take to get to 10? 1, 1, 2, 3, 4, 5. It took 5. So I'm gonna multiply 7 halves times 5. So here we go. 7 halves times 5 fifths. Minus, and then my 8 fifths. How many jumps did it take to get to 10th? 1, 2, only 2. So I'm gonna do 8 fifths times 2 halves, which is the same as saying, well, 7 times 5 is 35 tenths, and 8 times 2 is 16. 5 times 2 is 10. And again, yay, we have the same denominators, so we can just subtract like we know how to. So 35 minus 16. Let's see. I can't take 6 from 5. That doesn't exist. But I can decompose. That I can do. 15 minus 6 is 9. 2 minus 1 is 1. So we have 19 tenths. You could leave it like that, or how many wholes are in 19 tenths? What's 19 divided by 10? 1 whole, 10 pieces, and 9 left over. Okay, so that is our answers. We have two answers, 19 tenths or 1 and 9 tenths. They're the same thing. They are equivalent fractions. You can answer them either way. So here we have an area model representation of 2/4 plus 1/8. So as you can see that both of these rectangles are about the same size. So they both represent one whole. And 2/4 is shaded in over here. And 1/8 is shaded in here. Again, this is not perfect, but we do the best we can. So as you can see, they're cut differently. So it's really hard to know how much this is in total. How do we make these look the same? If you said a common denominator, you are right. You can see that this is cut into fourths, and this one is cut into eighths. They have different denominators, and it's really hard to compare two numbers that don't have the same denominator. Well, what can we do? Well, first I want to see what 4 and 8 have in common. 4, 8. Oops. 8 are hard to draw. They have 8 in common. So luckily, this one's already cut into eighths. We don't need to touch it. But how are we going to cut this rectangle into eighths? How would we cut this one into eighths? Well, I'm just going to cut it and see what happens. It tells me, the chart lets me know that I need to cut each segment into 2 pieces. So that's what I'm going to do. This segment gets cut into 2 pieces. This segment gets cut into 2 pieces. This one and this one. Let's see how many pieces there are now. 1, 2, 3, 4, 5, 6, 7, 8. They both have the same denominator now. Well, which green parts, how many green parts are in this rectangle that I just cut? Let's count. 1, 2, 3, 4. So this part is now 4/8. And so we're not calling it 2/4 anymore. We're going to call it 4/8 from now on. And this one was always 1/8. 4/8 plus 1/8 is 5/8. So our answer is 5/8. So as you can see, even with my area model representation, I still use the chart to see the multiples of the two denominators. You can either multiply them or do repeated addition, whatever it takes to get that chart. I think this problem says choose yes or no to tell whether the fraction is equivalent to 2/5. So it's just like what I just worked on, where I had a drawing and it's asking me, is it possible to change it into this denominator? Is it going to be able to change into an eighth or a tenth? So our denominator that we're working with is 5. So I'm going to list the multiples of 5. If a number is not a multiple of 5, I won't be able to cut it properly. So if it's not on this list, I can't cut it properly. So 5, 10, 15, 20, 25. Do you see any numbers on the list? Any denominators in A, B, C, D, or E that do not match any of these numbers? If it doesn't match, you know that one's an automatic no. It is not equivalent. Another way to check, because of course the numerator is important too. Another way to check is, if you do see the number on the chart, for example 10, how many jumps did it take to get there? 2. So you need to multiply by 2 on the top and the bottom, in the numerator and the denominator. So if you multiply with the numerator and it doesn't come out right, that's also a no. So let's do letter A together. Does the denominator check out? It does. There's a 10 right here. Now does the numerator check out? Is 2 times 2 4? It is. So that one's a yes. Keep going through the list and check off yes or no when you find an equivalent fraction. This problem is telling you that another way to find a common denominator is by multiplying the denominators, because of course it'll be common. They'll both appear on each other's charts. So for example, 5 and 4, they both will multiply by each other to get a common denominator. So for example, 5, 10, 15, 20. 4, 8, come on, 8, 12, 16, 20. So 5 times 4 is 20, and 4 times 5 is 20. So that's a really, really quick way to find a common denominator. It might not be your smallest one every single time, but it does work. So go ahead and multiply by the opposite denominator. So 5 times 4 gave us 20. So what's 3 times 4? 12. And 4 times 5 gave us 20. So what's 3 times 5? 15. So for the rest of them, simply multiply by the other denominator. 2 times 5 and 5 times 2. And make sure you're doing it on the numerator and the denominator. 8 times 6 and 6 times 8. This problem has more than one step. I'll show you why. Okay, so I'm going to use cubes to break down the problem. C, circle the numbers. Emil's backpack weighs 6 3/8 pounds. He removes a book that weighs 3/4 pounds. Then he removes a book that weighs 1/2 pound. How much does Emil's backpack weigh now? There's my question. How much does his backpack weigh after he took out those books? Box the math action words. I know remove means subtraction, and he does it twice. So we're going to subtract 2 times. I need to set up my equation. He has a backpack that weighs 6 3/8 pounds. He's going to take out a book, and then he takes out another book. And I need to know how much does his backpack weigh after that. Well, now I'm ready to solve, but I see a problem. All of these numbers have different denominators. What do they all have in common? I guess I should set up my chart. So I need a chart with 8, 4, and 2. So let's start with the smallest one and see if we can stop. 2, 4. Well, that's good. At least I know there's a 4 that they have in common. But what about the 8? Let's keep going. 2, 4, 6, 8. Okay, so at least I know the half can be written as 8ths. That'll be good. Let's do the same thing for 4. 4, 8. There it is, 8. And of course, 8 times 1 is 8. So they all have 8 in common. So I get to keep this number the same. I don't need to touch it if it already has an 8. But I need to change these two numbers, the 3/4 and the 1/2. Well, 3/4, how many jumps did it take to change that 4 into an 8? 1 jump, 2 jumps. It took 2 to get to 8. So I'm going to have to multiply by 2 halves. So when I get that number, I can subtract from 8. What about my 1/2? How many jumps does it take to get the half to change into 8ths? 1, 2, 3, 4. So I'm going to have to multiply 1/2 times 4/4. And when I get that, I'll be ready to I'll be ready to subtract. And this whole number here, how many 8ths are inside 6 wholes? How many 8ths are inside 6 wholes? So 8 plus 8 plus 8 plus 8 plus 8 plus 8. Figure that out and figure out how many 8ths are in this number altogether. And once you have all of those things ready to go, you'll be able to subtract. Good luck. This has been Lesson 10, Add and Subtract Fractions. Feel free to re-watch this video as many times as you need until you understand it. Go through the vocabulary, think about the benchmarks, practice adding and subtracting, and modeling of fractions.